Welcome back. In this short video, we're going to look at a mathematical concept that generally seems abstract to people who study it for the first time in college, but it is really just a rebuilding and a reframing of something that we know very well. I'll start with the definition of a basis. A collection of vectors makes a basis for a space or a subspace if they are linearly independent and they span the space. When I say they span the space, I mean that the span of those vectors is the whole space. So here I've just drawn a two-dimensional plane, something that we're probably very familiar with. And if I wanted two vectors that are linearly independent and span the space, well, I have infinitely many choices for those, but generally a natural selection would be the elementary vectors. Now, if you recall from the primer, when I write E with a subscript, I am referring to the vector of all zeros that has a 1 in the location indicated by the subscript. So E1 is the vector of zeros with a 1 in the first row, and E2 is the vector of zeros with the 1 in the second row. Okay, so these elementary vectors are a natural basis for the two-dimensional plane, R2. Coordinates are always represented in a basis. Okay, so here's where we're taking something elementary like coordinates and plotting points on a plane and bringing it into abstraction so that we can mess around with it a little bit to our advantage. So here I have the point 2, 3. Okay, we think about that as a vector, but also as a point. Now, each coordinate tells you how far to move along each basis direction. So when I have a 2 in a coordinate pair, I'm saying move 2 along the x-axis, or 2 times the length of E1. And the 3 tells me how far to move along, what we traditionally refer to as the y-axis, or 3 times E2. So this is a breakdown into parts according to the basis vectors. The 2 and the 3 here are the coordinates, but it's important to understand, and this was never highlighted in elementary education, that they are corresponding to certain basis directions. Here, E1 and E2 being what we usually think about as the positive x direction and the positive y direction. So again, this is itself a breakdown of that point, that vector, A, 2, 3, into parts along its basis directions. Now, I like to think about a troublemaker elementary student, who looks at this and likes to turn it on his head. And the teacher says, give me the coordinates of this point, and the rest of the class does what's listed there on the left. They say, well, that point is 2, 3. And this student says, nope, that point is -2, 3. Now, nothing in math is incorrect until you show your work. So when the typical students show their work, they show something like, well, we counted 2 along the x-axis and 3 along the y-axis. And what they're doing mathematically is what's shown here, using the elementary basis. But this student perhaps has the positive direction of x pointing the other way. And so when he does, he's correctly saying that we move -2 along the x-axis because the positive direction on his picture points to the left. Okay, so if the positive direction is over here, indeed, to get to this point, I should go -2 times V1 and 3 times V2, because here V2 is the same as E2. Both of these representations are perfectly fine and mathematically correct. In fact, the first is equal to the second. we just don't tend to think about V1 and V2 being our basis directions, but there's no reason for that. There's no axiom of mathematics that says, let positivity be on the right. In fact, you left-handed people should stand up against this because it's probably that way because most people are right-handed. So let's see if we can get some practice here. The first question asks, using this picture here, if I were to use these red vectors as my basis directions, what would be the signs of the coordinates of this green point? The second question, to find the coordinates of this vector x in the following basis. What you need to think about with both of these problems is just the definition that we're getting at here, which is that each point can be written as coordinates times basis vectors. So if you set up an expression that has a place for coordinates and a place for the basis vectors is equal to the point, you'll either generate a system of equations or just an expression that will help you think through these problems.